thanks again, Ben, for inviting me to this. This is a really cool opportunity. My first Twitch stream research presentation. I guess I can tell people I'm a Twitch streamer now. I like to talk today. Again, as Ben said, and gave a very kind introduction. I'm Dr. Tim Siegler, a current postdoc in the Hill House Group at the University of Texas, or the University of Washington, formerly of the Brian and Cole Group at the University of Texas at Austin. I want to present a little bit of my work that I did at the University of Texas, kind of scoping perovskite-CdTe tandems and seeing if that tandem architecture is a viable future, has a viable future, or is kind of a pipe dream and nothing more. And so let's begin. So to overcome the existential threat posed by anthropomorphic climate change without significant sacrifices to modern society, the first necessary step is a greening of the electricity sector, where we have to go to emission-free electricity generation as quickly as possible. Of emission-free electricity generation technologies, photovoltaics has the highest potential for transformative change with the fewest drawbacks to human health and the environment. And beyond this, PV has become one of the most dominant sources of electricity in the United States. Traditionally seen as an overly expensive technology, PV panel fabrication costs have exponentially decreased year over year, leading to record deployments, exponentially increasing deployments nationally and internationally. With a lot of this cost-driven growth being driven by reductions in the cost of the panel itself, the higher efficiency of the panel, which isn't directly intuitive, but if you think about it, if you can make two different panels, but one has at the same cost and one has higher efficiency than the other one, you're generating more electrons for a fixed cost. And since you don't care about the panel price, you care about the electron price, the price to get a current of electrons, that is going to, higher efficiency is by definition going to lead to lower prices, and is in fact the biggest driver, at least in the current meta, of cost reductions for PV technologies. And then longer module lifetime and higher reliability means that you're throwing away fewer panels as well, which has also contributed a significant amount to the cost reduction of these technologies. And by and large, this cost reduction has been consistent within a technology space. Incumbent technologies that have been around for 20 years or maybe 10 years, such as silicon, and in fact, almost exclusively silicon, is the dominant player in the market with 96% of global market share in 2017, and still likely much higher than 90% of global market share today. The only technologies that can even closely compete are thin film technologies that have also been around for a while, such as CdTe and copper indium gallium selenide. And this is good for society because we have an incumbent technology with a lot of research background and experience that has price points that are competitive with fossil fuels in almost every market nationally and internationally, ignoring storage as just from a generation standpoint, and increasingly even if you don't ignore storage in sunnier areas. But as kind of green photovoltaics researchers, it can at times feel a little bit like an existential threat. If silicon is indeed a winner, a technology that can compete by itself, do we even need alternative photovoltaic systems? Because silicon is already beating the traditional powerhouses, the fossil fuels, and the other types of electricity generation. And the and electrons are electrons. It doesn't really matter. Do we need alternative technologies? Some people might say no, but I think there's a couple areas where alternative photovoltaic generation technologies might be helpful. And there's two sort of avenues that I think can be filled by other technologies. First is the avenue of filling in specific niche needs that silicon cannot achieve, particularly in flexible and lightweight designs. Think about commercial products, this idea of ubiquitous photovoltaics, where photovoltaics are everywhere in every commercial product. Maybe these panels aren't hooked up to the grid, maybe these mini modules don't power more than a toaster oven, but they are ubiquitous, and therefore by powering small commercial products and acting as, let's say, portable chargers, you're reducing grid load in tiny chunks and helping to green electricity generation technologies. A little larger scale would be these permanently flexed designs that can be seamlessly incorporated in theory with a building integrated systems. So in architectural designs and other types of building technologies. These are interesting because they open up these new niche markets, but I think they could also provide some competition to silicon in certain areas if you look at a system-wide cost per electron for a number of different reasons. As panel cost exponentially decreases year over year over year, the overall cost of installing a PV panel is to a greater and greater degree dominated by costs that have nothing to do with the panel themselves, what we call balance of system costs, the balance of the system being all of the system that's not, well, the system, the PV itself. And the balance of system costs are from 60% up to 80 to 85% of the cost of installing a panel in most areas, meaning that whatever cost reductions you get on the panel side no longer make as big of an impact as they did 10 years ago. With these flexible designs, I believe, could potentially help with these balance of system costs. Imagine instead of having to hire a team of installers to lug a bunch of heavy silicon panels onto your rooftop, you could just buy a garden hose roll of flexible plastic-based photovoltaics from Home Depot, go to your roof, and do it yourself, hire an electrician to make sure you don't electrocute yourself and hook up to the grid correctly, but by and large, significantly saving on labor costs and overall installation costs as well as architectural design costs. As far as for this building integrated system, I think that these building integrated PV technologies, while they are a bit harder to implement because they have difficulty connecting into the grid, if this could be done at a competitive price point, there's a huge amount of advantage in terms of cost savings over the entire system. The way that PV is set up these days, you have large utility scale solar plants of hundreds of megawatts, that are in abandoned areas, abandoned cow pastures, the Sonoran Desert, the middle of the forest, a cleared area of the forest, basically away from where people are so that you can get economies of scale and eliminate those balance of system costs as much as you can. Then you have to connect those remote areas to population centers, which with high voltage transmission lines, which cost, as a heuristic measure, about $1 million for every mile of installed high voltage transmission line, which is not a very efficient way of sort of connecting the grid, although potentially could help grid operators manage load if there is a nationally or internationally connected grid, but nonetheless, it's still quite inefficient. Whereas these building integrated designs bring the electricity generation to the population center, allowing you to generate electricity on site and not have to worry about transmission, meaning higher reliability and resiliency. But actually, I just wanted to get that off my chest a little bit. I'm not really talking about flexible and permanently flexed designs. My idea for what alternative PV technologies can do is to actually not to compete with silicon, but rather to pair with silicon, what we call a tandem photovoltaic. The idea of a tandem photovoltaic is that you pair an existing technology, let's say silicon, for example, with a different technology that has a different optical energy gap or band gap. And when you do this, what you can do is you can take the wider band gap from an energy standpoint, so the higher energy band gap, and use this device as a top layer to absorb high energy photons And in so doing, you eliminate the amount of heat loss associated with absorption and conversion of these higher energy photons. You then take the lower band gap of your two material systems and you put that underneath the top cell, allowing you to capture a broader part, a larger percentage of the incident solar spectrum without having to worry about the normal trade-off where when you capture more light, you get more losses. Doing this sort of tandem PV technology can increase your theoretical efficiency from 34% up to 42%, which is a fairly significant improvement if it can be realized. There are two types of this tandem solar cell design. The simplest that you can conceive of is the 4-terminal design shown here, where you literally would take 2 different solar cells and stack them on top of each other. While this is easy and provides a lot of flexibility and even a marginally better efficiency and a lot more design flexibility as well, these systems are unlikely to ever be commercial because to really work as an effective 4-terminal tandem, these stacked architectures, they need to be electrically isolated from each other, which means that you have to double certain things, like you have to double your inverters that you install, your microinverters for each panel. You have to double the number of interconnects. You have to double a number of different balance of system costs when it comes to installation and the like that drive up balance of system costs to an unsustainable level, which, as I mentioned earlier, those are already quite high. So really what you want is these monolithic designs, if you can get them, where you have the one device directly placed in series in a direct stack on top of another device. So you get the benefit of having the 2 devices together, but to an installer, to an architect, to everybody else in the food chain, it's just one solar cell, despite the fact that it is technically 2 solar cells stacked on top of each other, which means your balance of system cost shouldn't go up, or at least won't go up by much if it does go up, and you get the added benefit of the additional, the boost in the theoretical thermodynamic limit for efficiency. And just to put a fine point on it, in case there's people who don't know, I'm going to be using specifically power conversion efficiency, or PCE. So if you see PCE throughout this talk, I'm referring to the efficiency of our devices. And the material that I want to use as an alternative PV or next-gen PV material are these halide perovskite devices. These perovskites are very promising optoelectronic materials for a number of different reasons, most promisingly because they can be deposited from solution. Unlike a traditional PV technology, these materials can be dissolved in common organic solvents, meaning that in theory you could print these solar cells as quickly, easily, and as flexibly as you would print a newspaper every morning or something like that, allowing for massive amounts of throughput and at very low cost. Perovskites are uniquely interesting because they have what we call defect tolerance, which means that you can deposit these very imperfect layers with a lot of atomistic dislocations and vacancies and things like this, and still somehow get very or passively efficient devices, whether it's photovoltaics, light emitting diodes, scintillation detectors for gamma ray detection, X-ray detection, or the like. It doesn't matter. You can get very high efficiencies with very imperfect layers, which is a rarity in solar cell materials. However, these perovskites have a lot of material limitations, like low environmental stability and non-uniformity over large areas, that need to be tackled before full implementation is realized. The perovskites themselves have this structure here, this cubic crystal structure with an organic A site, usually methyl ammonium, abbreviated Ma, or formamidium, a B site that consists primarily of lead with sometimes tin, and a halogen X site, usually iodide, but sometimes bromine, and even a little bit of chlorine from time to time. And perovskites are ideal for use in these monolithic tandem architectures for a number of different reasons. Their low cost means that you can actually realize the economic benefit of a higher efficiency panel, because you don't have to necessarily worry about the deposition of the perovskite itself being so expensive that it cancels out any efficiency gain you get. The low temperature processing of the perovskite layer means that you can employ these monolithic tandems, which, as I alluded to earlier, are much preferable to 4-terminal tandems, without having to worry about the deposition of the perovskite thermally damaging the underlying layers. With other types of PV technology, you often require temperature treatments of 250 C or higher, usually multiple, and usually about 500 C, but at least 250 C for most other technologies. This is very harmful for the silicon underlying cells, which can't withstand those annealing temperatures after they've been processed very well. And so perovskites, which can be annealed, which actually must be annealed at 100 degrees C or lower, allow for thermal compatibility to not be a problem with monolithic tandems of silicon or any other type of bottom cell technology. And then band gap tunability means that the current matching restriction that you need, basically the design inflexibility inherent to monolithic tandems I was alluding to earlier, to be easily matched with a judicious choice of halogen and A-side composition. To this, perovskites have been paired often and very successfully in tandem with silicon, copper, indium gallium selenide, other perovskites, CzTs, and even other types of next-gen PV technologies like organic PV and quantum dots. But surprisingly have not been paired with other popular PV materials, the biggest market share of which, CdTe, I will focus on today. CdTe solar cells have the second largest PV technology by market share, and this is largely limited. Their impact on the industry is largely limited by the fact there's only one company who really knows how to make an efficient CdTe solar cell in the entire world, and that is First Solar out of Denver, Golden, Colorado, in Colorado. And they do this in spite of having only the 5th highest record efficiency out there. CdTe is actually preferable to silicon solar cells in warm weather climates, such as in the American South, the global South, in North Africa, things like this, because they have much better efficiencies at higher temperatures relative to silicon, meaning that you can get cheaper electricity at these high temperatures with a CdTe device. So, when me and my collaborators from Colorado State University were looking at trying to see, well, is there a way to make a perovskite CdTe tandem that would work? The first important consideration was design of the tandem cell itself. And so we started with the base architectures in the perovskite and CdTe cells. Perovskite cells don't have to have this architecture, and in fact, most of the tandem architectures aren't quite like this, but nonetheless, perovskites usually adopt some sort of pin architecture with an N-type contact layer transporting electrons away from the device after they're photoexcited. In this case, that's TiO2. A P-type organic transport layer, in this case spiral OMI-TAD, to shuttle away holes from the perovskite, where holes are just basically electronic states where electron should be and isn't because the electron got excited by light. And then so that's the perovskite junction with then metal contacts on top and bottom. And then the CdTe device is a more simple traditional P-N heterojunction with a CdTe P-type layer, a selenium backgrating that in optimal devices has a minimum band gap of 1.42 near the junction, and then a window layer, an N-type contact layer that has traditionally been Cad selenide, but in recent years has been moving more towards I think it's magnesium zinc oxide to create wider band gap window layer contact materials so that more light can get through to the CdTe device. So, with this in mind, potential architecture considerations, we wanted to rule out as many of the architectures as possible based on just design constraints given the current state of perovskite and CdTe fields. And the first one, and it's kind of a major unfortunate blow, is that perovskites cannot be used in this sort of top cell arrangement with CdTe. The reason is you really want this arrangement here, where CdTe is the top cell, even though it's shown on the bottom here, light is shining from below in this instance, you really do want the cadmium telluride to be the quote-unquote top cell, because it has a wider band gap. That 1.42 EV, it is on the wider side of acceptable band gap ranges. So a really good CdTe tandem would have CdTe as the wider band gap material and a different narrow band gap device. Unfortunately, the range of known photovoltaic perovskites, it bottoms out at 1.17 EV, which is only 0.2 electron volts lower than the perovskite band gap. And every material that has band gaps between, let's say 1.4 and 1.17, are tremendously unstable to the point that they're almost unusable, which is a further complication of this issue. Ideally, you'd want a really stable 0.8 to 0.95 EV band gap material as the pairing for CdTe. As it stands, perovskites can't achieve that, asterisk. We'll talk about that later. But CdTe cannot be the top cell. Further complicating things is that the CdTe is indeed a traditional p-n junction. And unlike p-n junctions in textbooks, the optical path, the optical depth of the CdTe and its junction layer are not the same. And so therefore you need photovoltaic light to be incident on this junction first. If you shine light from the top of the CdTe cell from the opposite side of the junction, what happens is that light that's traveling through, that's supposed to be absorbed by the cadmium telluride, gets absorbed in this shocky junction region of the device right here, and leaving almost no photon flux at this back interface, where flux is tremendously important. Because there is no light here, the depletion region does not set up in this device as it normally should be, or as it normally does, meaning you have very inefficient CdTe devices that can't actually be used and are very, very inefficient. And so unfortunately, this monolithic architecture is not possible, and as well as this four-terminal architecture because of this design restriction. And then the final consideration is this the last monolithic architecture that could potentially be, that hasn't been eliminated yet by the other two design restrictions, is unfortunately impossible due to thermal compatibility issues, which I alluded to earlier when motivating perovskites as ideal monolithic tandem pairings. Cadmium telluride requires 2 processing steps in excess of 500 C, requiring a total of about an hour's worth of annealing time at these temperatures, which means that if you were going to try to deposit a cadmium telluride layer on a completed perovskite device, you would completely degrade this perovskite, which has a thermal decomposition of about 220, really about 120, but nonetheless, it has rapid decomposition about 220. And this spiral omega layer will completely turn to carbon ash at about 100 degrees C. And so you can't, unfortunately, do a monolithic tandem with CdTe and perovskite, given the current state of both technologies. The only feasible architecture really is this suboptimal 4-terminal tandem. To sum up all the reasons why I say suboptimal, the CdTe is the narrow band gap material in this tandem, which it should be the wider band gap material, but perovskites don't go low enough. And the 4 terminals are commercially less viable because of the increased balance of system costs, meaning that it is unfortunately probably not going to be very attractive for PV developers in the field. The third thing that I haven't mentioned yet is that in order to use this type of architecture, we have to go away from the super high efficiency perovskite devices that people have used in the past and move to these wide band gap bromide-based devices. In this case, methyl ammonium lead bromide is the perovskite, which means that the 20 to 25% efficiency you may know perovskites solar cells normally achieve cannot be achieved in our top cell, which only has a world record efficiency of 11%. Not all is lost, however. There are advantages to a 4-terminal architecture. It's easier to optimize. You avoid thermal compatibility issues, which means that can deposit TiO2 using traditional methods, and it has a higher theoretical PCE. And so what we did is we took us and our collaborators, we wanted to just make a really, really suboptimal device and just see what happened. And that's exactly what we did. We made perovskite-CdTe 4-terminal tandems, and we saw they had originally very low PCE, which we attributed to the fact that we hadn't optimized our methylammonium lead bromide fabrication procedure yet. But interestingly, we saw that there was another design consideration we hadn't normally accounted for, hadn't expected. And that is this current loss between CdTe by itself without perovskite and CdTe with the perovskite in the tandem. Now, you expect current loss when you have a tandem solar cell. That's just the nature of being the narrow bandgap material. Some of the light you would normally absorb if the top cell wasn't there is being absorbed and converted by the top cell. But the percentage of this light that has been taken by the perovskite is about 50% higher than we would normally want it to be. And so because of this considerable light loss, we wanted to characterize exactly what was going on in this top cell that caused the significant light loss. In other words, what is throttling the direct transmission of light below the band gap of our methyl ammonium lead bromide? Again, above the band gap, you would have this light being absorbed by the perovskite material and converted to electricity. But you'd want all the light that's below the energy of the band gap of methyl ammonium lead bromide to directly go in this direct transmission bin and be incident on the invisible cadmium telluride device that you on the right side of the screen here. In reality, you have a lot of mechanisms that can contribute to loss of throttling of this direct transmission, including direct reflectance, specular reflectance of incident light, and these scattering processes, diffuse reflectance and diffuse transmittance, which come about due to surface roughness and interfaces when light sees a lot of different indices of refraction in very close proximity, and therefore light is then reflected in a random orientation in 3 space off of your sample. So to figure out exactly what was going on, we took our perovskite devices and we took each individual layer and did transmission measurements on them and saw a significant amount of transmission in the region of interest, 850 to the bandgap of the perovskite, 850 is the bandgap of the CdTe. And we saw most of the light losses we were observing are in the perovskite layer itself. Taking the perovskite layer, which has this weird glossy look to it, atypical of perovskites that have narrower band gap, to a diffuse reflectance accessory, we saw that we had a lot of these scattering processes that were contributing to a significant, an unacceptably high, in fact, portion of the transmittance loss in these devices. And so this was very unfortunate and something that we were thinking about characterizing. Because if others were to also try to use this material in a tandem, this is an important consideration that they'd have to wrestle with. To characterize this optical haze, so to speak, in the system, we use polarized light microscopy, a regular light microscopy technique with 2 polarizers on either side of your sample that have rotating axes relative to each other. For this technique, there are 2 measurements of interest. When source and sensor polarization vector lines are lined up with each other, they are in parallel, and you get what approximates a normal light microscopy image, a bright field image. But when source and sensor polarizer are rotated relative to each other 90 degrees, you'd expect to see, based on elementary physics, just a completely black square. If in the cross-polarized case, as we call it, there is an image that appears, that means there's an interaction of the polarization vector of your incident light with your sample. This happens most frequently in the literature because of a birefringence effect. When you have a largely anisotropic material, basically anisotropic meaning different directions, not uniform in 3 different directions. So you have this anisotropic material that has different indices of refraction along the symmetric and asymmetric axes that cause your light to sort of bend 90 degrees in polarization space in your sample, causing you to see an image in the reflected, in the cross-polarized case. And this can happen either due to crystal structure anisotropy or because you have this nanowire structure, and that can actually cause a birefringence effect even in symmetric crystals. We have neither nanowires in our sample, nor do we have an anisotropic crystal. Our crystal is perfectly cubic. And so if we were to see a cross-polarized, any image in the cross-polarized case, it would have to be as a result of scattering, as scattering can randomize the polarization vector of incident light as this light goes through 2 or more scattering processes very efficiently. Indeed, we see that we get an image in the cross-polarized case. It has a negative correlation with the intensity of the parallel polarized case. And we see that this haze that we're observing in our UV spectrum, our UV vis spectrum, are localized on these surface ridges, which others have characterized in the literature as a wrinkling of the thin film. Which is particularly problematic with these wide bandgap materials, which is why we, working with these bromide materials, have had problems with this, whereas the iodide-based material systems, people working with those have not had quite as many problems. And using SEM, we were able to see that these ridges are present there as well and are clear topography of the film and not some sort of local dielectric change. So then what we did is we took a 15.5% efficient CdTe device in the semiconductor capacitance simulator, a all-in-one 1D device simulator. The model had been optimized by our collaborators at Colorado State, and we wanted to see exactly how much haze could be tolerated in a perovskite CdTe cell before the CdTe cell would be better off without the perovskite whatsoever and would just be better standing by itself. These are the results that we got. And we have this very aggressive curve that you see right here. Now, remind you, this curve only goes up as you go from 15.5% efficiency to 18, 19, 20% efficiency. The mean efficiency of the panels at First Solar has pushed out in their most recent generation of panel devices. Nonetheless, even at this suboptimal efficiency, you still have a very aggressive curve at the kind of hazes that are present in traditional spin coating processes. You need near world record efficiencies, which the world record is 10.9%. At least the verifiable world record, I'd say, is 10.9%, to achieve the kind of performance that you would get in a where you get just even a marginal improvement in the tandem solar silicon efficiency compared to CdTe. And if you can try to find a way to smooth the micron scale morphology out of the MAPBR, you can get to a regime where you have a wider window of efficiency improvement, but even so, you need about 6-7% really good efficiencies to even think about improving the efficiency of the tandem. And then you have to consider the economic consideration, which is, can we make this so much more efficient that the additional cost of making the MAPBR solar cell is worth it? We get more electrons out to justify the cost, and that becomes a bit of a especially in a 4-terminal, of a hairy proposition. Indeed, it appears that MAPBR just really, at the moment, doesn't have really good tandem pairing potential with any type of technology, as we get similarly aggressive curves for a lot of other tandems that have ready simulations in the semiconductor capacitance simulation software setup. But we did learn from this is that control of morphology is important if MAPBR is to be used in tandem solar cells, whether that be perovskite-perovskite or whether that be CdTe-perovskite tandems. And while micron scale morphology proved very difficult to tune in solution process systems, we were able to improve morphology a bit using crystal texture control on the nanoscale by adding a bit of silver into our precursor solutions. Crystal texture is important for a variety of different mechanical and electrical properties and improving them in optoelectronic devices. And in perovskites, this control over crystal texture is normally done by adding these long organic carbocations, these 2D spacers, so to speak, which, while doing a great job of controlling morphology and actually improving stability of the perovskites, are significant hindrances to the electrical transport through these films. Fewer studies have shown that you can get this similar sort of crystal texture with the B-site additive. And we showed that adding monovalent silver to our precursor solution induced very strong uniform 001 ordering in our thin films from these apparent randomly oriented grains in the silver-free cases of spin coating deposition. And these are on silicon substrates. Integrating this 001 peak as a function of azimuth angle, we're able to see that, in fact, we don't have perfectly randomly oriented grains without silver. We actually have weak 011 oriented grains that soon get replaced with a very strong 001 ordering with successive amounts of silver addition into our thin films. Amazingly, we're able to do this on any substrate we choose, showing this has nothing to do with the specific interactions of the perovskite layer with the silicon substrate. We're able to do this on amorphous silicon glass, we're able to do this on ITO-coated glass, and we're even able to repeat the exact results I've just shown on mesoporous substrates like mesoporous TiO2, which I showed earlier was the N-type layer used in most photovoltaic perovskite materials, or devices, rather, sorry. To figure out exactly what was going on, we turned to composition heterogeneity as an answer to our issues, with the idea being perhaps silver was somehow changing the relative surface energy of different facets. To first examine this, we took XPS and EDS, two different elemental techniques of all of our different silver mole percent inclusive MAPBR thin films. And this is important because these two techniques have different penetration depths and therefore probe different parts of the film. EDS has a penetration depth that is long enough to get the entire bulk of our film multiple times over. It is a few microns, tens of microns in thickness, whereas our thin film is about 300 nanometers, whereas XPS is a very surface sensitive technique and only has about 10 nanometers of penetration depth. Therefore is only probing the silver, the elemental composition very near to the front interface of our thin film. Up to 5% silver incorporation, our XPS counts of silver are much higher than our EDS counts, showing that, at least in these samples, we have preferential silver segregation to the specific interfaces of our thin film. Now, that's less important than the back interface, which potentially could be even more important in driving this order. So to probe silver depth to probe the elemental composition of the depth of our film, we took these TOF SIMS profiles. We performed a time of flight time of flight secondary ion mass spectrometry measurement on each of our thin films, with the idea being you have this elemental sputtering probe that generates these secondary ions that are taken to a time of flight analyzer, analyzed by mass, and then we can compare the fragments that come off at different depths through our film to characterize exactly what's happening. We did these on ITO substrates in order to minimize the amount of charging in our sample and also to protect our perovskite from silicon, because there are silicon bromide fragments with the same molar mass as our silver. It's yes, silicon bromide, that's right, with the same molar mass as silver, which complicates spectrum. But we tracked 3 different species. We tracked methyl ammonium lead bromide, indium tin oxide, and silver as well. And we saw, amazingly, at each of these, for each of these thin films, that at the interface of the methyl ammonium lead bromide and the indium tin oxide, silver counts started to spike pretty amazingly, indicating that we had, for however strong our and this was irrespective of the amount of silver in our precursor solution, showing that however much front surface segregation we had with the silver, we had even stronger back surface segregation of the silver, showing us somewhat convincingly that we were indeed getting silver to segregate 2 interfaces and not incorporating the bulk, but in so doing, changing the relative surface energy of 001 facets relative to other facets and driving uniform texture in our thin film through this surface energy anisotropy. Sadly, this does not lead to better devices. In fact, it led to much worse devices. But this is not due to the increased order of our film, but rather due to the emergence above 1% silver incorporation of these unfortunate secondary phases. The benefit of silver not incorporating into the bulk of your crystal is that you can get this segregation that induces this order, but the unfortunate consequence is that you have these secondary phases that emerge as well. They're rich in silver. You can see them differently in the contrast in even bare SEM. And you can even see their crystal, you can do crystallography on them and see their crystal peak, or see their peaks in X-ray diffraction or grazing incidence, wide angle X-ray scattering as well. Unfortunately, we aren't able to identify this material based solely on X-ray scattering. There are no peaks in the crystallography database that correspond to these different peaks that emerge in our GUX patterns. And furthermore, we weren't able to, either through solid state or solution phase synthesis methods, generate bulk thin films or powders of this impurity phase. And so we weren't able to fully characterize it. But to do a little bit more characterization, we went back to the TOF-SIMs, sputtered off the first 10 nanometers of our film, and then took a very high resolution TOF-SIMs profile of a 1 to 2 nanometer slice of our thin film that was, again, 10 nanometers down from the very front surface. And we wanted to see what the 2D heterogeneity in these different elements were, where we saw that these secondary domains that appeared in, I believe this is a 5% silver inclusive sample, were rich in lead, rich in silver, as the SEM, or as the EDX spectra previously had shown us, but surprisingly and interestingly lacked any organics at all, any amines, I should rather say, indicating that this is some previously unidentified phase in the silver-lead-bromine phase diagram that potentially someone else could, either through metastable methods, through strain or something, synthesize in the future and identify as a potential loss. This could also be interesting for degradation experiments on PV devices, as these silver-lead-bromide phases could be contributing to performance loss in those as well. So unfortunately, it does not improve micron scale morphology the way doing the silver doping the way it improves nanoscale morphology. And so methyl ammonium lead bromide might be a non-starter when trying to make cadmium telluride tandem devices. So alternatives are considered, and we did a little bit of work to try to consider some of these alternatives. And we wanted to do so by challenging that very first precept I talked about in the design of perovskite-CdTe tandems, the idea that there is no perovskite that has a band gap below 1.1 eV. Indeed, there is no perovskite that has been employed in a solar cell with a band gap that low, but halfway through this process of working on these previous results, several papers came out in the double perovskite single crystal community showing that we had several different materials that had band gaps in the 1 eV range or below. Of the materials that were the 2 to 4 materials that were identified, we wanted to focus on cesium, silver, thallium bromide because A, it was a direct gap material, B, it had a band gap of below 1 eV, the only material that had such a low band gap, and 3, it didn't rely on these dopant additives, these inorganic additives, to reduce the band gap. Oftentimes in these crystals, in these perovskite materials, when you have this dopant that is responsible for a significant amount of band gap reduction, it's hard to tell if that is due to true electronic band gap reduction or just a reduction in the apparent optical band gap, as because of spin relaxation due to spin orbit coupling or parity relaxation or some other quantum mechanic effect, these dopants can actually have optically active defect bands that contribute significantly to absorption in your devices. So you actually, this absorption could be due to this bulk crystal, or could be, as in the case of bismuth doped methyl ammonium lead bromide, just direct absorption to a defect band that doesn't contribute electrically to whatever device you want it to make with this material. And so to avoid that risk, we went with the cesium, silver, thallium bromide. However, working with thallium poses its own risks. Thallium is the most toxic non-radioactive element on the periodic table, and traditional perovskite spin coat processing require you to complex these metals with organic polar solvents like dimethylformamide and dimethyl sulfoxide that permeate skin very readily. Therefore, even in a controlled lab environment with very high safety standards, working with thallium in a bulk perovskite spin coating process is a safety non-starter. So to avoid these problems, we tried to tackle this by leveraging an existing collaboration with the Joey Luther Group, the world experts on perovskite nanocrystal devices, to try to develop nanocrystal synthesis of this material for eventual deposition in solar cells and deployment ultimately in CdTe tandem PV. So to try to synthesize this material, we employed a strategy from the Gamelin group. We could not employ the traditional Kovalenko method of perovskite nanocrystal synthesis because trivalent thallium bromide is thermodynamically unstable. When it is formed metastably, it easily, within a couple of seconds or minutes, disproportionates and creates thallium-1 bromide and elemental bromine. So we used instead acetate precursors, including this trivalent thallium. Remember throughout this whole talk, this is a trivalent thallium species, and a ready bromine donor, trimethyl bromide, as the injection material to complete our reaction. And in our system, we also had a solvent, inactive solvent of octadecene, as well as these this ligand co-pair, oleic acid and olealamine, the latter of which is super crucial for making nanocrystals as opposed to bulk powders, which is something that's also going to come up through this last part of the talk. Cesium silver thallium bromide synthesis was not as easy as just taking the bromide, the bismuth out of the Gamelin reaction and adding thallium back in. So to try to work up to making cesium silver thallium bromide, we started with just trying to make thallium bromide nanocrystals, work our way up to thallium silver bromide nanocrystals, and then hopefully achieve these CATB nanocrystals we were really hoping for. Doing this with thallium bromide, we were able to make these super uniform spherical thallium bromide particles with very uniform sizes, smaller than anyone's been able to make before. These materials could potentially be used in radiation detection applications. They already are. And so this is very exciting to get these nice uniform nanocrystals. We're able to show that we could tune the size distribution of these nanocrystals over a limited temperature range by just increasing reaction temperature above 170 degrees C. You had rapid aggregation and crashing from solution, so you had no nanoparticulate product in your final reaction, or at least no nanoparticulate product that could survive any amount of watching or processing whatsoever. And in fact, these nanocrystals were so uniform, they formed these extended superlattice networks, these 1-1-1 superlattices, these FCC superlattices with uniform 1-1-1 orientation on your substrates as well. The dithallium silver bromide nanocrystals also had this nice uniform semi-spherical orientation, though could not be uniformly tuned. And this was the first time anyone has been able to show that they could synthesize this material, this crystal, in nanocrystal form. As it is a relatively unstudied material, we also were the first ones to report the optical band gap of thallium silver bromide and got a band gap of 3.07 electron volts in an indirect gap material from Kubelka-Munk analysis. There was a large Urbach tail in the system, which we attribute either to anti-site defects, as the sample was silver rich and thallium poor by EDS, or potentially anharmonicity in the band structure of thallium silver bromide. Again, it's not a very well studied system, and this is a common problem that creates these large sub-band gap absorption tails in high Z systems. Amazingly, when we switched from trivalent thallium precursors to monovalent thallium, we ended up with these very non-uniform crystals. We were still able to get nanocrystals, but they had very large, not that large of a size non-uniformity, but a large amount of shape non-uniformity. In the case of thallium silver bromide, had real, even stronger propensity to aggregate than in the trivalent system, leading to these very ugly-looking nanoparticles, indicating there's something special about trivalent precursors that lead to more uniform orientation and superlattice formation in these nanocrystal systems. Unfortunately, I don't have good news about the final step that we were hoping to achieve. After many, many, many attempts, it appears that we can't use current nanocrystal synthesis methods to get cesium silver thallium bromide nanocrystals. We find that thallium 3+ reduces almost immediately to thallium 1+ when exposed to the amine ligand, which is very important for getting nanocrystals out of your reaction mixture. Even when this amine is replaced or eliminated to just get basic powders, the resultant products are usually the 3,2,9 motif of the cesium silver thallium bromide, as well as, even without the amine, a bunch of 1+ contaminant products like thallium bromide and thallium silver bromide. So some other way of making nanocrystals, some tricks with thermodynamics and kinetics, and potentially even non-colloidal methods, like a microwave method of some kind that no one has used in perovskites before, are going to be needed if someone wants to really use this material in PV devices or in CdTe tandems. So in conclusion, I don't know if perovskite CdTe tandems are ever going to be a thing. They're too similar in band gap, the CdTe and the workhorse perovskite technologies, to be used effectively as tandem, easily in tandems. The wide band gap materials that you could potentially pair with CdTe have very low efficiency loss tolerance to achieve efficient devices, and a large amount of optical loss in the sub-band gap region that totally deflects incident light and hinders the development of tandem technologies. And lower band gap materials that exist right now cannot safely be deployed, synthesized, and deposited in PV devices, given traditional methods of nanocrystal synthesis. So new material discovery, which is still ongoing and very promising. There's a recent report of a low band gap quad perovskite from the Solis Sabara group that struck my attention right as I was leaving Texas. Those are going to be needed if perovskite CdTe tandems are truly going to have a chance at commercialization, as you need those narrow band gap perovskites for these monolithic integrations that would be necessary for commercial products. So with that, these are all the citations to the work I presented on today. I'd like to acknowledge everybody who helped with my project, all the people on the papers that I mentioned earlier and who helped me with all these experiments. My current boss, Dr. Hillhouse, Professor Hillhouse, my collaborators at Colorado State, Olajubat Sampath and Tushar Shimpi, collaborators at Texas A&M University Central Texas, Professor Taylor Harvey and Dr. Ida Tarabi. They have a very powerful it's an unknown university. It actually just started in 2015, and they, Dr. Harvey, Professor Harvey, has a very powerful SEM, EDS, and electroluminescence system where you might not expect to see it at this small local college, commuter college in the middle of Texas. So check out Texas A&M Central Texas if you're interested in doing some electroluminescence spectra. I'm sure Dr. Harvey would love to collaborate with you. And then this is my old group and Brian A. Korgel group, Equinor, who sponsored most of this work. Very cool oil company to be doing this, as well as the DoD and Next Gen Photovoltaic Center, and my current employer, person who pays the bills, the CEDO office of the U.S. Department of Energy. With that, I'd like to ask any questions or answer any questions that you may have throughout this presentation. Thank you so much for having me tonight.
All right, thank you for coming on, Tim. That was a fantastic presentation and a nice balance of both educational and informative, and you know, some nice fundamental science, as well as some really good information about the commercial viability. So while everybody in chat is, while any questions trickle in from there, I have a couple that I'd like to ask. So can you talk a little bit about it was almost like a wide angle XRD, but it had the azimuth technique. That's not one I'm familiar with. Can you talk about it a little bit more?
Yeah, so it's easy enough to see. So the way you would observe crystal texture normally is you just look at this peak and you see if there's a spot versus a ring. If there's a ring, you have this random uniform texture. If there's a spot, there's oriented texture in a specific direction. And with this color map, it's with any color map, truly, the eyes deceive. And so what I really wanted to do is we took a certain range of 2 theta or Q between this Q here. I think it's about maybe 11 or 12, doesn't exactly matter, and the Q ring here. And we integrated X-ray counts as a function of the azimuth angle, basically the angle from, so this would be an azimuth of 0, this would be an azimuth of 90, this would be 180.
Okay.
And doing that, we could more easily see the orientations of our thin films. Took a little bit of processing to filter some of the noise out, but this is much more illustrative in showing us that we have, based on where the X-ray intensity peaks along that azimuth, we have much more insight and don't have to rely on our deceiving eyes to figure out the orientations.
Yeah, that's really interesting. Like I said, that's not one. I mean, I've seen, glancing angle and the wide angle and all that. I've never seen the azimuth measurement before, so that's a really interesting way to do it.
But yeah, it still is using the grazing incidence technique. Okay. It's just a post-processing way of better visualization, I would say.
Yeah, absolutely. That's a really interesting way to do it.
Yeah.
So with the tandem devices, are there any options for? Because I know one of the things that you had mentioned was, that some of the issue was that, like, the photons going through the perovskite cell would you would absorb some of them there, or they'd be reflected or something like that. Could you willingly make one of the cells thinner than you normally would to deal with something like that, or is the loss that you get from doing that more than what you might gain, if that makes sense?
Yeah, no, I mean, that's something I tried very hard to do. The problem is it's impossible. It's very difficult. And I did a lot of different things to try to make this happen, through thinning the layer in a number of different ways, like spin coat speed or concentrations, or even compositional changes and things of that nature. But no matter what, what I found is when you make your layer thinner, you introduce a bunch of these pinholes. And the pinholes, for those unfamiliar with PVs, those are device killers. And so your device goes to basically zero efficiency, unfortunately. I mean, not actually, but it's very
Effectively.
difficult to come back from that.
Yeah.
Yeah. And you do get a lot. You gain a lot of transmission, not just in the sub-band gap region, but in the above band gap region, which can also be absorbed by your CdTe absorber. But yeah, no, you can't meet a minimum efficiency threshold using that technique. So unfortunately.
Okay. Are there any options? I mean, as you pointed out, the advantage of CAD Telluride is that it's an established technology. The efficiencies in commercial processes even are very high. Are there people looking at like tandem perovskites?
Yes, we're actually. I think that we there's a group here. There's a startup here in Washington, Swift Solar, that's trying to look at all perovskite tandems. That's been something people are looking at as well. The idea being that you could do both. So if you look at like the two paths to commercialization, which if you see some of my other talks on YouTube, catered to a more general audience, I'll talk about that in more detail. You can do both these things. You can have a tandem device with very high efficiency sub devices, and then also potentially have this flexible, lightweight design. So do both those things at once. And so there is interest in these all perovskite tandems, but as you start getting to these all perovskite tandems, you really have to concern yourself with cell reliability and stability, and that becomes a really significant issue because a lot of
Sure.
these require tin incorporation and divalent tin. And if you've ever tried to take divalent tin into the universe, you know tin does not want to be divalent; it wants to be quadrivalent, so it will
Yes.
oxidize immediately. So this is something that they have to contend with.
Okay. This is an interesting set of challenges. There are
Mhm.
so many, excuse me, competing issues to deal with. It's so, and some of it's pretty straightforward, like you said, aligning a low band gap material with a high band gap and that kind of stuff. Like that's intuitive, but then some of these other things not so much.
Yeah, yeah. So I think it's good to talk about these things too. I mean,
Oh yeah.
just a general research philosophy, it's not all about the successful results. It can also be about what didn't work and why it didn't work, because I think that can be illustrative as well.
Yeah, absolutely. You need to be able to be honest about what's going to work and what's not.
Yep.
Um, so do you have an idea? You talked about the difficulty in synthesizing that final perovskite with the cesium silver.
Gallium bromide.
Yeah.
Yeah.
Do you have any ideas on potential techniques that may allow you to synthesize it? Because
Yeah.
I know you said like you may need a non-colloidal method or something like that. Are there any um, so you can do like sulfurization methods or something like that where you put like elemental sulfur in, heat it up a little bit, vaporize it, and that makes it reactive enough to do something. Is there something along those lines, or is there some other method that you're thinking of?
Yeah, I can answer this a number of different ways. First, that kind of sulfurization method, like a analogous halogenation method,
Mm-hmm.
wouldn't work for these systems because they're so reactive. You need to be able to quench it within 5 seconds of reaction time,
Oh wow.
and you can't really do that with a gas phase system.
Yeah.
Colloidal system, the strategies I have, and I hope someone picks this up, but I don't think they will because of just how toxic thallium is. Um, is involve a lot of long shots. First off, I think the only way you're going to be able to make this system is you're going to have to make the chlorine nanoparticles and then use the bromine precursor to do a halogen exchange, which has
Okay.
been shown to work very well. Um, I think that's because of the very high standard reduction potential of trivalent thallium. If you expose trivalent thallium to unreacted Br minus in just standard conditions, not in a crystal, in just standard conditions, um, you're going to get a redox couple between those two species where you have elemental bromine pop out and monovalent thallium. Um, I think that you get to do a couple things. First, I think that you have to do the reaction in oxygen. I don't think a normal Schlinkline technique where you do it in nitrogen is actually going to be the answer. and somehow trying to avoid oxide species being formed while you do that might be a significant challenge. Secondly, you're going to have to stay away from amines, which is something that perovskite nanocrystal folks really don't love to do, even in well-established systems. So you're going to have to use some of the Liberato mana methods of, let's say, a phosphenic acid of some kind, or some Zwitter ionic ligand, but incorporate that in the reaction mixture, which is going to be an expensive proposition. And I mean, now, and potentially quite difficult to optimize. But I think that there is something out there. There might be a way of doing this. I speak regularly whenever I'm at a conference with Hema Karunadasa, the Stanford inorganic chemist who she came up with this composition. She tells me it's very possible and I should be able to do it every time I talk to her. I mean, and she's very good at her job, so I think that she could do it, but I mean, she's not a nanocrystal person, but you know, it's something that I think can be done. It's just someone smarter than me is going to have to figure out how to do it.
Okay, that's fair. That's it's a big challenge to do. Is there any possibility of doing like a co-deposition, like a co-sputtering deposition or something like that, and getting them to react, or is it?
Yeah, no, that would be the other method. It would be I'd say evaporation is probably good enough. It's way gentler. You wouldn't damage your species with these halogen-based things, but reproducibility in thermal evap depositions is a huge problem. I think, as you know, being formerly of the Buddy Mullins group and interacting with some of the perovskite
that's
team there.
Very true, yeah.
Yeah, and secondly, I don't know how to exhaust gaseous thallium. I don't like that proposition.
That's a fair point. That's a fair point.
Yes. That seems like another toxicity concern. So
yeah, very much so. Yeah, I can't imagine that's something they're going to want going up the hood. That would be that's asking for trouble.
Or out the chimney or into the room.
Yeah, exactly. Yeah. I always forget. That's one of my favorite things. I was like, yeah, where do these hoods come out? And there's like, oh, just right on top of the building. Like, oh, okay, cool. Good to know. Thanks, guys. That explains the smells sometimes.
Exactly. Yeah.
Oh my god. Oh, jeez. Yeah. This is really fascinating stuff. I want to see if I don't know if there's any more questions that have been asked. If not, I think I still have a couple.
Okay. All right.
Shoot, now the train of thought left me. Up and disappeared. Oh, okay. So with when you had the thallium-1 precursors, you kind of mentioned that it seemed like the thallium-3 was what got you like the super lattices and the better size distribution and shape distribution. Do you have a feel for why that is, or is that kind of still an open question?
It's still a fairly open question. I didn't do too much exploring with the thallium-1 precursors. It is, in fact, the thallium-1 is the real toxic stuff. Even in metallic and trivalent thallium, the danger is, well, it could oxidize or reduce to thallium-1.
Okay.
And so I didn't want to play around too much with this synthesis. I kind of just replicated my same reaction conditions with the monovalent thallium precursors and saw these things. I think there's some interesting, if you look very, very closely, perhaps too closely, one might say, at these TEM images, you see that you get sort of faceting, right? Where you look at, you can almost see a couple cubes intermixed with some.
Yes, I see a triangle in there too.
Yeah, so this could be an instance where these, at least in thallium, I think in thallium silver bromide, these things have, these nanocrystals in general have such a propensity, even in the trivalent case, to aggregate, that you need as much help as you can to avoid aggregation, where the monovalent is just a hopeless cause. But in the TLBR nanocrystals, I think there's an interesting faceting project hidden somewhere in there, where using monovalent versus trivalent precursors, you can get different shape. You can get shape control for some reason that's still to be determined. So yeah.
It never hurts to look for side projects. So
yeah, exactly.
That's interesting. Yeah, you're right. Looking at this one, looking at the TLBR, I mean, like you said, I see spheres, cubes, and triangles. So certainly,
Yeah,
if you could control it, that
that'd
could
be
be
interesting.
interesting. Yeah,
Yeah, right.
that's very cool. All right, I'll give a last chance real quick. Anybody have some questions? I think that might be it. So with that, Tim, I will go ahead and say thank you for coming on. I really appreciate it.
Yes.
It was
Yep.
a fantastic talk. I figured it would
Yep.
be, and it was. It was, like I said, it was very interesting to see the combination of the fundamental work and then how you applied it to sort of the broader commercialization questions. Because as you pointed out, that's kind of, that's an important consideration. You can learn all kinds of interesting things, but it also is helpful to be able to apply it somewhere down the line, even if you hadn't been doing it yourself. That's still something that is good to have at least an eye on along the way.
Yep. And thanks for having me. It was fun and interesting to do it this way. So
Yeah,
yep.
absolutely, and I hope you'll come back on at a later date. Anytime you would like to come on, we would love to have you.
All right, perfect. Great.
Awesome.
Thank
Well,
you.
thank you, and thank you everybody for coming out to watch. This is Open Science Presentations, and if you liked what you saw here, like I said, the stream will be edited down to just the talk and the Q&A and uploaded to YouTube. Please feel free to join our Discord. The links for that are all right below the stream. And if you are interested in giving a presentation yourself, please feel free to DM me on Discord or send me an email, meekins@sc.edu, meekins@sc.edu. And I think that's going to be all for tonight. So thank you all for coming. Thank you again to Dr. Tim Siegler, for his presentation. And I hope you all have a good night and a good weekend.
Thanks, everyone.